Dear Chairman, dear all guests, my name is Rok Ambrožič and I am PhD student in Faculty of Chemistry and Chemical Technology at University of Ljubljana, Slovenia. In my PhD study I develop new bio-based polymers which can be used instead of classic petrol-based materials. Anyway, before I begin, I believe I should explain a little bit more from where exactly I came from. Slovenia is a small country, somewhere here in the central Europe, situated between Italy, Austria, Croatia and Hungary. Our faculty is placed in Ljubljana, which is the capital and the largest city of Slovenia. Meanwhile, now we are somewhere here, I believe. Here is a concept of my presentation. First I will look at our basic idea of our study, then I will talk a little bit of how the research was done, then the results will be discussed, and at the end I will talk a little bit of our future plans and future projects. Few words of the benzoxazines. Benzoxazines are novel thermosetting resins which can be synthesized from phenols, primary amines and formaldehyde. First paper where benzoxazine synthesis was reported was published in 1944, but benzoxazine has not been extensively studied until late 1980s or early 1990s. Polybenzoxazines, on the other hand, are formed by ring opening polymerization of benzoxazine precursors. Why are so special? First of all, they are very versatile, so its properties can be easily modified. Therefore, polybenzoxazines have been introduced in various fields of application, such as surfactant, as composite materials, materials with enhanced flame retardancy, material for self-healing and aerospace application, and so on. All this was possible because of their excellent mechanical and thermal properties, such as high strength and high glass transition temperature. The main disadvantages of polybenzoxazines are relatively high temperature of curing and low cross-link density, resulting in material brittleness. Idea of our study, we try to use the advantages and improve the disadvantages of polybenzoxazines by preparing novel bio-based polybenzoxazine with enhanced cross-link densities. Because of the great flexibility in the molecular design, benzoxazine monomers can be prepared exclusively from bio-based static materials, which is desirable due to environmental issue. Bio-based monomers were prepared from natural phenols like cardanol and from natural amines like furfurylamine. On the other hand, higher cross-link density was achieved by higher monomer functionality or by introducing additional groups that can polymerize, such as furan or epoxy groups, into monomer molecule. Synthesis, the cardanol, the natural phenol, was the basic for preparation of all benzoxazine monomers. The benzoxazine from cardanol, aniline and paraformaldehyde was used as a reference sample. To synthesize monomer with additional furan group, furfurylamine was used, and to synthesize monomer with additional oxazine group, bisfunctional amine was used. Different synthesis path was designed for preparation monomer with additional epoxy groups. Firstly, unsaturated side chain of the cardanol was epoxidized using hydrogen peroxide and acetic acid. Secondly, epoxidized cardanol reacted with aniline and paraformaldehyde to form modified benzoxazine monomer with additional epoxy groups. By determination of epoxy equivalent weight, it was found out that conversion of double bonds into epoxide was around 60%, and that vast majority of that epoxy groups remain unreacted after synthesis to benzoxazine. All the structure was also confirmed by ER and NMR analysis. Curing process of all monomers were studied using differential scanning calorimetry. Polymerization of benzoxazine is thermally initiated. The oxazine ring is opened by the cleavage of CO bond, and the molecule is transformed from closed ring to open linear chain structure. This intermediate then reacts with aromatic ring of another monomer molecule to form cross ring network. Polymerization of benzoxazine is autocatalyzed as newly produced hydroxyl group act as additional accelerator for ring opening of oxazine rings. What is more, free phenolic groups may also react with epoxy groups, which were in our cases present in benzoxazines modified with epoxide. Curing process of all monomers were observed above 200 degrees of Celsius. The narrowest curing range and the higher temperature of curing were observed for monomers without additional furan or epoxy groups, meaning only oxazine groups were involved in curing. Meanwhile, curing process of benzoxazine with additional furan or epoxy groups showed a broader temperature range and larger amount of heat was released, indicating additional curing reaction were occurring. Few authors already reported curing mechanism of benzoxazine containing conditional furan groups. They suggested that furan compounds participate in benzoxazine ring opening polymerization by electrophilic aromatic substitution, resulting in additional linkage to furan group. On the other hand, copolymerization between epoxide and oxazine has been extensively studied. After oxazine ring is opened, free hydroxyl group are formed, which can then polymerize with epoxide. Bisfunctional monomer also show pronounced melting transition in early temperature. Curing kinetic, results of curing kinetic further confirm previous results. Curing kinetic were studied by applying different kinetic methods such as Kissinger method and Flynn-Wall-Zawa method. This method do not require prior knowledge of reaction mechanism to quantify the apparent activation energy, which is only the function of degree of polymerization. Mechanical and viscoelastic properties were examined by dynamical mechanical analysis. All measurements were taken on rectangular specimens using shear testing mode. Two pieces of sample, this is the red one, were placed between three plates. The side plates were fixed while the middle plates oscillated to generate shear deformation. All samples were transformed from glassy state at room temperature through glass transition into a rubbery plateau at higher temperature. All polymers, with the exception of the one with additional epoxy groups, showed similar value of storage modulus in the glassy state. Meanwhile, polymer with additional epoxy groups had higher value of storage modulus, indicating higher stiffness of its structure. In the rubbery region, considerably different value of storage modulus for each sample were observed, indicating different crosslink densities. Glass transition temperature increased parallel with increasing storage modulus in the rubbery plateau. The higher TG was also associated with lower and broader peak of loss factor, indicating more elastic behavior and higher heterogeneity of the system. Crosslink density is defined as the number of network chain per volume unit in the crude material. According to theory of rubbery elasticity, the degree of crosslink density vary according to the value of storage modulus in the rubbery plateau. As expected from DMA results, the lowest crosslink density, which was calculated according to Wright-on equation, was found for a reference sample without additional groups that can polymerize. Meanwhile, additional furan, oxazine, and especially epoxy groups clearly increased the value of crosslink density, what consequently improved mechanical properties of polymers. So our thesis, which was set at the beginning of our study, was in fact confirmed, since novel bio-based polybenzoxazine with enhanced crosslink densities were prepared by modification with furan, oxazine, and especially epoxy groups. So, to conclude, novel bio-based benzoxazine were prepared from cardanol. Monomers have been modified in such a way to contain additional furan, oxazine, or epoxy groups, which try to improve the low crosslink density of polybenzoxazine, which is responsible for material brittleness. With monomer modification, higher value of crosslink densities were achieved, which should improve the brittleness of material epoxy modifications has proved to be the best way to generate advanced material, since it not only gave the highest value of cross-link density, but also the highest value of storage modulus and glass transition temperature. Plans and ideas. Recently our group is working on bio-based benzoxazine with emulsified properties, which can be used to stabilize aqueous emulsions. Since epoxy resins show great compatibility with benzoxazine resin, we prepare epoxy aqueous emulsions. Dispersed phase containing epoxy resins was mixed with continuous phase containing water and benzoxazine surfactant to obtain stable aqueous emulsions. These emulsions were then dried and cured at elevated temperature. During curing, benzoxazine and epoxy resin copolymerized to form cured coating. Since reactive surfactant was used, no voids were formed in the coating, what consequently improved mechanical properties of coating, especially their hardness. Additional benefit, if more green coating is desirable, is also possibility of replacing synthetic epoxy resin with bio-based one, such as epoxidized soybean oil. So this is basically it. I have to thank all of my colleagues. Special thanks go to University of Ljubljana and our Ministry of Education, Science and Sports for financial support. And of course, thank you all for your attention. Now I'm available for your question.